Hello everybody, today we're going to be taking a look at this problem. We are going to be today figuring out how to determine whether a binary search tree is balanced or unbalanced. So first of all, let's first off look at the problem statement to define what a balanced binary search tree is. We reviewed binary search trees at one point. I don't know. I don't think we even mentioned a binary search tree, but you guys might have heard of it, and I'll explain the definition of that in particular. But what a balanced binary search tree is, it's a type of binary search tree where the nodes are arranged so that the height, longest path from the root to a leaf is kept as small as possible, ensuring operations like search, insertion, and deletion stay efficient, typically big O of log n time complexity. The balanced part means that the tree shape is roughly symmetric. It doesn't need to be completely symmetrical like we did with one other problem, if you guys remember checking if a binary tree is symmetric, but it has to be roughly symmetric. The left and right subtrees of every node have to have similar height, not necessarily exactly the same, but within a small bound. For this specific problem, this small bound that we're going to be setting is going to be a value of one node. So I can put that in, one node difference. This prevents the tree from degenerating into a linked list, which would make operations big O of n. So hopefully you guys kind of get the idea of what I'm saying already, but in case you don't, I'm going to switch to the whiteboard. So now here we have two examples of binary search trees. So how a binary search tree works is that like every other type of tree, it's filled with these nodes that are connected together. And in a binary tree, a binary search tree is a specific type of binary tree. Each node is connected to two nodes, and in a binary search tree in particular, for every node, the entire left subtree actually is going to be less than the node. So for example, this 4, everything to the left is less than it, and everything to the right is greater than it. So you see how 2, 1, 2, 3 is less than 4, 6, 5, 7 is greater than 4. Same thing for the number 2. Everything to the left of 2 is less than 2. Everything to the right of 2 is greater than 2. So that's essentially what a binary search tree is. However, you can see on this side here, I should have circled these earlier, but you can see based off of this, if you take a look at this tree, it technically qualifies as a binary tree because a binary tree is defined by every node having at least, not at least, at most two connecting nodes. So it could have at most two connecting nodes, but it could also only have one connecting node. And every node in a binary search tree, every node to the right is greater and every node to the left is less. However, in this instance, every node to the right of each node is greater. So both of these are binary search trees. However, it's pretty obvious which of these two, if I were to ask you, which of these two are balanced. This is a balanced binary search tree, but this is not. So we're trying to figure out what the difference is between these two. How do we get to a balanced binary search tree? So here is the formula that I'm going to be setting. Essentially, what we're going to be setting is that a binary search tree is balanced. BST is balanced if the height of the left subtree, I'll say LST, is minus the height of RST, the right subtree, is less than or equal to 1. Specifically, the absolute value is less than or equal to 1. So what this means is if the left subtree is, like, for example, if there was an additional thing, like let's say there's the number 9, this would still be a balanced subtree because the right subtree is going to be only one node greater than the height of the left subtree. So the height of this subtree is 2, the height of this subtree is 3, but because they're in the same range, this is still going to be a balanced binary search tree. So that's what we are going to be defining as a balanced binary search tree. Now, how do we go about calculating this? So to start off, what we want to make sure is that, one, we're going to be recursively going through starting from the root node, and we're going to be checking the height of the left subtree and then the right subtree. Next, we need to make sure that the left subtree and the right subtree have a height difference that is less than or equal to 1, like in the formula. And yeah, if we know that that it's balanced, if we know that that's true, then we can simply return the output as true. Return true. I think that's enough explanation. Hopefully the visual representation somewhat helped you guys. So we can start going back to the code. Alright, so here we have the code. So first, I'm just going to copy paste this. I've used this for several tree problems. This is how you define a tree node. A tree node consists of a self value, a value of the number, in this case the integer that is in the node, and then there's going to be a pointer to the left node, and then there's going to be a pointer to the right node. And that's how we define a tree node. Next, let's make our function. We're going to call our function isBalanced, and we are going to simply start by putting in the root. This entire function is going to be called on any node with the root as the input, and it's supposed to return true or false. So the way we're going to be doing this is we're going to be doing this recursively. So in a recursive function, this isn't always the case, but it is good to have a helper function because we are going to be doing an operation called check to see whether this a tree is balanced. The binary tree is balanced. And why we're going to be doing this recursively is that we're not only going to be checking the entire tree itself, but we're also going to be calling this check command on the left subtree and then the right subtree, and we're going to be continuously doing that. So the first thing we need to know is that if not node, what does not node mean? It means that simply if there is no node. So this is the base condition. It means that the tree is done. There's no tree left, and it could be at the beginning, it could be the first element, the first root that we get, or it could be one of the last roots. But essentially, when we see that there's nothing else to go to, then obviously an empty tree is also a balanced tree because there's nothing on the left or there's nothing on the right. It's just 0, 0. So that's the same thing as being balanced. So we're going to be returning true. But what we're not going to just be returning true, we can have a comma here in Python. I'm not sure if you guys are familiar with this, but you can return not just true, but we're also going to be returning an integer. And this integer is going to be the height of the tree. So we're going to be returning true and the height of the tree, which in this case is going to be 0. Next, what we're going to be doing is we're going to be splitting this up into the left subtree and then the right subtree. So remember how I said we're going to be calling it recursively? So what we're going to be doing is check node.left and check node.right. And we are going to be setting these to to variables. We're going to be setting it to a thing called left balanced and then right balanced. But hold on right now. What you might realize is that since we are in this base condition, for example, we are not just returning one value, we are returning two values. So we're going to also be returning another thing called left underscore height. So what we're returning is we're going to be returning two data values. One is going to be whether or not the tree is balanced and what exactly the tree's height is. And if you remember, why are we calculating, why do we want both of these? Well, obviously we want to know whether the tree is balanced, but we also need the height because our entire formula for calculating whether or not a binary search tree is balanced is this formula. Height is we're making sure that the height of the left subtree and the height of the right subtree are in the range of, don't have a range of more than 1. So let's go back to the code, and we're going to be doing right balanced and then right underscore height. Alright, so there we go. Now finally we're going to be once we've done the left subtree and then the right subtree recursively, what is our final output going to be? So what we're going to be doing is we're going to be having a final thing that we're going to be returning, which is balanced. Is the tree balanced or not? And what we're going to be defining balanced as is it's going to be a combination of, we need to make sure that a tree is balanced if both the left subtree is balanced and the right subtree is balanced. So we're going to say this and this. So we need to know that the left subtree is balanced, and then not left, we're going and right is balanced. And then one more function, which is the same function that we had earlier in the whiteboard. We need to make sure that the absolute value of the height of the left subtree and then the right subtree is less than or equal to 1. And how we do that in Python is pretty simple. We use the abs value because that's equivalent to the absolute value, left height minus right height. And if you don't know about absolute value, it essentially means that if left height is, for example, 1 and then the right height is 2, 1 minus 2 is -1, but absolute value always results in a positive result, so this would be 1. Absolute value is determined to get the positive difference between these two values. So we get these positive two values between these between the left and right height, and what we want to ensure is that it's not greater than 1. So we're going to be putting this entire thing, absolute value of left height and right height is less than or equal to 1. So that's our third condition. These are all the three conditions that need to be true in order to determine whether or not a binary search tree is going to be balanced. Alright, so that's essentially how our recursive function works. At the end, we can simply return balanced. Oh, sorry about that. I forgot to mention, what we're going to actually be doing is we're going to be returning within this recursive function itself, we're going to be returning balanced, and also to calculate the height of the tree, which is the whole point of this, is we're trying to also calculate to make sure that the heights of the two subtrees are even. What we're going to be doing is we're going to be adding 1 plus the max value of the left height and the right height. So what does this mean? Well, obviously it's obvious why we want to return balanced, because we want to return the Boolean value of whether or not it's true or false. However, to calculate this part, the absolute value of the left height and the right height, we need to calculate the left and right height. However, what we see is that obviously we know that if there's no tree at all, the height is going to be 0. However, otherwise, how do we calculate the height of a tree? Well, if we go to the whiteboard again, a height of the tree is essentially the distance between the root node and the lowest possible child node, right? So, for example, in this tree right here, I know it's kind of messy. I'll try to draw it again really quickly. 1, 3, 6, 5, 7, 9. Essentially, the height of this tree is going to be 1, 2, 3. Actually, it's actually going to be 4, actually. You don't calculate just the nodes. We're not just the lines, the edges between the nodes. We're calculating the nodes itself. So 1, 2, 3, 4. 4. Yeah, you get the idea. Basically, the height of this tree is going to be 4, but how do we get to that? We check the distance between the left subtree, and then you see how, the root has a left subtree and a right subtree, right? However, we see that the right subtree is clearly larger, and to do that, well, that means that we have to ignore the left subtree entirely in this case and focus on only the right subtree. So we calculate 1, we have the root node, and then we calculate the height of the maximum of the right subtree. We focus on the right subtree because the right subtree has a higher height, and we add that 1 to the root. And we do this continuously for every single node. That's essentially how we calculate the height of a tree. Maybe in a future video we might go more in depth into how exactly a height of the tree works, but essentially this is how you calculate the height of a tree. You calculate the left subtree height, the right subtree height recursively by using the check of node.left. If the node is if there is no node, you return 0. Otherwise, you return 1 plus the max, the 1 plus the whichever subtree is bigger, the left subtree or the right subtree. And yeah, that's essentially it. You need to make sure that that's essentially how you calculate the height of the left and right subtrees. You have to make sure that they're both have a difference of less than or equal to 1. And then at the end, sorry, this video is getting a little bit longer than I expected, but we're almost done. Now that we've finished our internal check function, finally, outside of this check function, we can return check of root. Alright, so now let's test the code to see if it's right. I'm gonna copy paste this thing since we're running a little bit short on time. So we see here we have this first tree that is similar to the one that I have in the whiteboard here. It's going to be having 4, 2, 1, 3, 6, 5, 7, and if we do the call the isBalance function of this one, what we should expect is that we get the output of true because this tree is balanced. However, this tree is not balanced. This is the 1, 2, 3 tree that I did in the whiteboard. The 1, 2, 3 on the right here. This one. And that is not a balanced binary search tree, so we're going to be returning false there. So let's run the code just to test if it works. And yeah, there we go. The code actually returned a list because it also returned the height of the subtree, the height of the tree as well. So you can't ignore that by just putting this 0, and that would just get out whether or not it's a balanced or not subtree, and you see we get true or false. So yeah, true and false, because the first example is true, the second example is false. Alright, it was a bit of a long explanation, kind of a doozy, but hopefully you guys got a thorough understanding of what a binary search tree is, first of all, and then what a balanced binary search tree is. Also, it's important to note the reason for why we're doing this. A balanced binary search tree is way easier to do operations in because of the fact that, for example, a search algorithm, of like starting, if you wanted to find the number 3, the number 3 is a bad example because in both cases you'd be able to find it in 3 steps, in 2 steps technically. But the difference is that in a binary search tree that is balanced, the operations are going to be much less because you have like this even split of numbers. It will take log n time complexity to search into a binary search tree that is balanced, whereas if it's not balanced, it could be up to n, as we mentioned in the beginning here, because you'd have to go through essentially the entire tree just to find a single value. So yeah, that's essentially it. Hopefully you guys understood the explanation I gave, and see you guys in the next one. See ya.